So here's another counting question that comes up often enough that we've got formulas to help us think about it. So the question would be, how many different sets of k is a variable, items can be chosen from a set of n items? Okay, so that question, the answer to that question is sometimes called it's called a combination. So how many combinations of k items can we choose from a broader set of n items? And this only makes sense, of course, when k is a smaller number than n. We call the answer to that n choose k. And as we're going to see, we write this as n over k in parentheses. So this expression that we're going to talk about very, very shortly, you would read n choose k if you encounter that on a page. So using a standard strategy here, let's pick some numbers that are small enough that we can see what's going on under the hood, and use that example to understand a formula that will apply to bigger numbers. So our example will be, how many different committees of 3 people can be chosen from a group of 5. Okay, so we've got 5 people. We have to select 3 of them for a committee. How many different ways are there to do that? And just as we did with permutations, let's just start off by listing them. Okay, so to list them, let's give our people names. So let's call our people person A, B, C, D, and E. That gets us to 5. And okay, let's kind of be systematic. Let's sort of first list the committees that have person A. Okay, so we can have person A and B and C, person A and B and D, person A and C and D. I left out one here, person A, B, and E. You can tell I've got a little kind of systematic order in mind here. So far I've done 3 committees that have A and B. These are all the possibilities with A and B. Okay. Now I'm looking at the ones that don't have B, but have A and C in them. So we've got ACD. We also have ACE. Those are all the ones with A and C here. That's this one, this one, and this one. And then we've got one that doesn't have either C or D. And those are all the possibilities for committees that include person A. Okay, so 6 committees of 3 with person A. Fine, but we have to have A, so let's go on and keep counting. So let's look for some with B, but not A, because we've got all the ones with A, obviously. So we can have person B, C, and D. We can have B, C, and E. Okay, and we can have B, D, and E. And that's actually all the ones that we have that have B but not A. So 3 there. And now we also want to look at how many without B and A. And it turns out there's just one left. Okay, if we don't have, sorry, that was supposed to be B and A. Let me write that appropriately. If we don't have B and we don't have A, because we've taken care of all the ones with A, all the ones with B, then we're only left with 3 people, and so they all have to be on the committee. Okay. Use my enumerating color here, CDE, so there is 1. Okay. So there's a total of 6 plus 3 plus 1, 10 committees of 3 from the larger set of 5 people. Okay. All right, so that looks good. As I said, I was sort of trying to be systematic and listing them here. Even though 3 and 5 are pretty small numbers, I kind of had to go in a pattern to make sure I wasn't leaving anything out. So first I did all the ones that have A and B. There were 3. And then I had the ones that had A and C, but not B. There were 2, and that left me just 1 more that had A, not B and C and D. And so this is kind of just this sort of ad hoc counting method that I'm doing in my mind, but that's sort of the root of the more systematic formula. So now let's go to another board here and think more systematically about this. But I'm still in this example here. So systematically, let's kind of think of the steps here, the way we did with permutations. Okay, so we have 5 total people. That means we have 5 choices for the first person on the committee. For the first slot. And then once that person's decided, then there's 4 more. 4 for the second. And then we have 3 choices for the third. Okay, so this seems to imply that we should have 5 times 4 times 3 equals 60 possible committees. That's not what we got before. It's way more, right? We only got 10 here when we enumerated. Okay, so let's think about what's going on. Well, when we're enumerating here, we were only thinking about committees where the first position was A, B, or C, but that's not actually a problem because I could have written them in any order here. The committee that has person D first is the same as the committee that has person D last. They're sets. These committees that we're choosing are sets. They're not ordered. Okay, so we have a problem here of overcounting. Okay, this idea of looking at the different possibilities for first, second, and third, this method treats ABC, CBA, BCA, BAC, CAB, ACB, treats all of those differently. Treats them as different committees. From our point of view, they're the same. Okay, it doesn't really, this first slot, we're using it to sort of be systematic, but it doesn't really matter. In the problem, these 6 should count as just 1. Okay, now that reconciles it, right? Because when we just enumerated, our answer was 10. And when we tried to be systematic, but had this problem of overcounting, we were over by a factor of 6. So if we divide out the 6, then we'll get the correct answer here. Okay, so count for this by dividing, and 60 divided by 6 does equal 10. Okay. Okay, so what's the general idea here? Let's give myself a little bit of space here to write the general form. Choose K from N. Let's go through what we did. We've got this sort of N choices for first place, N minus 1 for second, N minus 2 for third. And we're just going to correct it at the end by dividing out the number of ways to order K items. That sounds kind of familiar, doesn't it? But let's write it. Okay. So we have choices for first, N minus 1 for second. We're going to repeat that K times, then divide by the number of ways of arranging the K items, the number of ways that we can write them in the different order, but for this, the order doesn't matter. Okay, so the answer here is going to be N times N minus 1, N minus 2, dot, dot, dot. And my dot, dot, dot here is going to be determined by however many factors I want to have. I want to have K factors in this numerator. And then I'm going to divide it by, let's go back to my main color here, divide it by K factorial. In fact, I want to get rid of this one blue line that is bugging me. Didn't want to have it here. Okay. This is, in fact, the formula for N choose K. So N choose K has K factors in the numerator, and it starts with N, and you just sort of march down one integer at a time. And the denominator is corrects for the different orderings. Okay. And this is a perfectly fine way to write the formula for N choose K. It's the part of it that we don't like is, in general in math, we don't like this ellipsis dot, dot, dot thing. So let's be a little more systematic about it. So let's carve myself out a little more board here. Okay. And let's think about what we've got here. We've got, it looks like N factorial, but it doesn't go all the way down to 1, right? It's N factorial with the last K factors removed, right? So we could just divide them out. We could rewrite the numerator here as N times, actually, yeah, I'll write it this way. N minus 1, N minus 2, all the way down to 1, divided by N minus K, all the way down to 1. Okay. We could write it as N divided by N minus K factorial. But we also have to remember that we're dividing by K factorial as well. All right. We're going to go to a new page, and I'll rewrite this formula in the way that you normally see it. So N choose K is N factorial with the last K terms removed here, divided by K factorial to correct for order. Okay, so this is the correction for overcounting. This denominator here and this compound fraction are the factors not included because we only have K, right? We're not ordering all N of them. We're only ordering the first k of them. So we're just dividing out those other factors. And the way you would normally see this written is to have the denominators consolidated here. So n factorial times n minus k factorial times k factorial. This is what you would sort of see in most books for the combinatoric formula, it might be called. It's also called binomial coefficient. These numbers appear other places in math. They are these n choose k numbers. They're all integers, of course, because they're based on integers. They have interesting patterns. They're kind of cool in their own right, and they pop up places other than probability as well. But this counting formula is why we're interested in them. What I was doing here in this kind of belaboring this point is I think the standard formula can be hard to wrap your brain around because we're used to thinking of the numerator meaning one thing and the denominator meaning another. And that's not actually what's going on here. Here, this part of it, the n factorial divided by n minus k factorial, is just telling us to start at n and multiply n by the k, starting with n, that would be the k minus 1 integers smaller than it. So this part of the whole expression is just designed to get rid of that dot, dot, dot part. And then this part of the denominator corrects for the overcounting. ABC is different from CBA and BCA, etc. Okay. So reminding ourselves of the example that we had, where we had 5 choose 3. Okay. Remember, we talked ourselves into thinking, well, it should be 5 times 4 times 3. That got us to 60. That was too big. And then we realized, oh, we have to count. We have to account for the fact that order doesn't matter. So that was why we divided by the number of different ways we could order the 3 slots, divided by 3 factorial. And then in figuring out how to write this compactly, what we did with 5, 4, and the 3 is we wrote that as 5 factorial divided by 5 minus 3, which is 2 factorial. Okay. And let's just put in the numbers there and make sure that it all works the way we think it's going to. So 5 factorial is 5, is 4 times 3 times 2 to 1. 5 minus 3 factorial is 2 times 1. And 3 factorial is 3 times 2 times 1. And let's go ahead and just cancel terms here. So cancel this, and so I get 5 times 4 divided by 2 does indeed equal 10. Okay, so this formula, the number of ways of selecting an unordered set of k from a larger group of n items, is going to come up in helping us understand some of the kind of famous discrete random variables that describe situations that come up over and over again. So we're going to see that in the next unit. Just a couple of ending comments here. One that I sort of alluded to at the beginning, calling this a combination has never helped me. It's, in my mind, not all that close to the ordinary language usage of combination. But what really helps me is remembering that this is called n choose k, because that's exactly tells you what it is. You have n, you're choosing k, how many ways can you do it? That's what the formula is telling you. Another thing that you might be wondering about is sometimes we might actually care about the bigger numbers. Sometimes we might actually want an ordered set. So the main example I can think of in real life is in racing sports, people will talk about podiums, like how many different ways are there to choose first, second, and third place from a set of, say, 10 racers. And in that kind of situation, you really care about who the first, second, and third places are. So just finishing up where that interruption left off. I was saying that the calling it a combination wasn't super helpful for me. Thinking of it as n choose k is helpful. I was also saying that there are some contexts in which we don't want to do this correction of making order not matter. Sometimes we do want to treat A in first, B in second, C in third as differently from C in first, A in second, and B in third. When we do, if order does matter, there's a formula for that too. It's simpler because we had it on our way to this one. It's called K permutation. That's the number of ordered sets of K from a larger set of n. And that is just n factorial divided by n minus k factorial. Okay, so if it was how many podiums, if you will, where you're thinking that it matters, like it matters if you're the people on the podium, whether you're getting gold, silver, or bronze there, the number would be 5 times 4 times 3. Okay, and that is indeed 5 factorial divided by 5 minus 3 factorial. So 5 factorial with the last two factors divided out. And as I said, going back to the regular n choose k, the order doesn't matter scenario, those are also called binomial coefficients. You may run into them in other contexts, and we'll be seeing them in Unit 6 as part of probability distributions.